Welcome to my class. I'm Drew Coulomb. In our previous lecture, we were examining variation, direct variation and indirect variation. This is when you have two phenomena and they're related to each other. With direct variation, if one variable goes up, the other one goes up as well. If that variable goes down, the other variable goes down in response. With indirect variation, it is the opposite. If one value goes up, in response, the other value goes down. And if one value goes down, in response, the other value goes up. When we were examining these variables, we were looking at two variables only. This is not a real-world situation. Quite often, there can be many variables in play, and changes in these variables can affect all the other variables. That's where combined variation comes in. Let's examine that now. So combined variation is when we are examining one variable and its relationship to more than one other variable. Again, this is more real-world applicable. Let's build on the knowledge we used last day, and we will look at our first example. The force between two electrically charged particles, Q1 and Q2, varies directly as the product of the two charges. Write the equation. So our variables, we have force, we have charge 1, we have charge 2. It says they vary directly. Force is directly proportional to the product of Q1 and Q2. We can then turn that into equation by replacing our proportionality symbol with equals our constant of proportionality. Force is equal to K times Q1 Q2. You can see here the relationship between the force and the charges on two particles. There's actually a law called Coulomb's law. Force equals K times Q1 Q2 over radius squared. So there's an extra variable in there, but this is actually a formula. It's called Coulomb's law. And if you're going to study physics, you'll learn some of this. So here we would have to add in an additional variable. Let's examine the next one. Express the equation for the fact that y varies directly as x and inversely as z. So I'm comparing y to x and I'm comparing y to z. So here, y is directly proportional to x and y is inversely proportional to z. So here I have two statements. What do I do now? What I can do is I can combine them into one statement. Y is proportional to x over z. See what I did there? All I did was just multiply these together. To build the equation, y is equal to kx over z. So I've replaced my proportionality symbol with my equals k. So here's three different variables. One varies directly and one varies inversely. Let's examine the next one. Express the equation for the fact that s varies directly as the square of t and inversely as the cube of v. So I'm relating s to t, and I'm relating s to v. Notice I have extra words here, square and the cube, very important. So let's build that. So I have s varying directly with t, but not just t squared. And I have s varying inversely with v, but not just v cubed. Just like before, combine these together into one equation. S is proportional to t squared over v cubed. Finally, replace our proportionality symbol with our equals k, our constant of proportionality. S is equal to k t squared over v cubed. As you can see, building these equations is not very difficult. Let's look at a real example you might be working with, say in chemistry. The pressure P of a gas varies directly as the temperature T, and inversely with the volume V. Next up, I've given you a situation where I've given you the temperature, the volume, and the pressure with the units. I've now asked you to solve for the pressure when the temperature is this and the volume is that. Step number 1, let's build our equation. So pressure varies directly as temperature. Pressure is proportional to temperature. It's directly proportional. So I'm comparing pressure to temperature, and I'm going to compare pressure to volume. How is pressure related to volume? Well, it is inversely proportional to volume. Again, we will combine these together to build one equation. Pressure is proportional to temperature over volume. We can then build an equation. Pressure is equal to K times T over V. And then what I can do is I can solve for K. K is equal to PV over T. If I knew what PV and T was, I could solve this. I have that now, I could solve for K. However, what I'm going to do here is I'm going to use our 2-point proportionality to solve this. Let's build an equation. So this is a constant. So if I have a pressure and a volume and a temperature, and I have a different situation, those two things are equal. This is actually a formula you'll use in chemistry. This is called your combined gas law. That's why I built this equation using 2-point proportionality, because this is the formula you may have to memorize. I want you to see where it comes from. Let's now solve this. So here I have a situation where I have the pressure, the volume, and the temperature. Finally, I've asked for what the pressure is. I've given you the temperature and the volume. So you can see there are 6 variables here. I know 5 of them. Sub those in and solve for the one unknown. What I'm going to do first, I'm going to rearrange my equation first before I sub in my values. It can be a challenge moving values around with the units, and mistakes can be made. So if you have many variables, I would advise you to rearrange first. Let's do that now. P2 is equal to P1 V1 over T1. The T moves from the bottom to the top, and the V moves from the top to the bottom. So here I get T2, and on the bottom I get V2. Let's sub in the values we do know. P1 was 30 psi. V1, 200 inches cubed. Now I have T2. What's T2? It's right here, 70 degrees Celsius. On the bottom here, I have T1. It's right here, 50 degrees Celsius, and I have V2, 300 inches cubed. Now notice what happens here. I have inches cubed on the top and inches cubed on the bottom. They cancel each other out. I have degrees Celsius on the bottom and on the top. They cancel each other out, leaving me with PSI. So my final pressure, the units will be in PSI. Please note that you must have the same units on the top and the bottom for them to cancel each other out. If I gave you the temperature in degrees Celsius for one unit, and in the other situation I gave you temperature in degrees Fahrenheit, you must convert them both to degrees Celsius or degrees Fahrenheit so that they cancel each other out. Also take note that oftentimes these equations only work when those units are certain units. For instance, this may only work when it's in degrees Celsius, not when in Fahrenheit or Kelvin. So you might want to double check before you start switching between other units. Let's now solve this. Pressure 2 is equal to 28 psi. If you're dealing with significant digits, we could say that 0 was significant, that was significant, and that was significant, and that was significant. Let's say those are all significant, in which case you would round off to 2 significant digits, 28 psi. Therefore, the pressure was 28 psi. Later on, you're going to use other formulas. For instance, PV equals nRT, the ideal gas law. This right here, this is a constant. This would be like your constant of proportionality, but it's actually a known constant. You'll learn about this in your chemistry class later on. Let's examine some other situations. Force of a moving object varies directly with the product of its mass and its acceleration. Meaning, force varies directly as mass times acceleration. I can turn that into equation. Force equals kma. If I make k equal to 1, force equals mass times acceleration. This is actually Newton's second law. This is a real formula. Let's examine this now. If the mass remains constant, what happens to the force when the acceleration is cut in half? So here we have force is equal to our constant times our mass times our acceleration. It says here that mass remains constant and our constant proportionality, it remains constant as well. So if I cut my acceleration in half, what happens to my force? It's also cut in half. So you can see as this decreases as well. However, the mass remains the same. Let's look at a very similar situation, but in the other direction. Force equals constant times mass times acceleration. For the same object, what force will happen when the acceleration is tripled? Same object, mass is constant, and my constant is constant. If I multiply this by 3, I have to multiply that by 3 as well. Again, as I increase this variable acceleration, my force also increases. Which is why on an airplane, during takeoff, you're pushed back in your seat. You have a lot of acceleration, causes a lot of force on your body. Now let's examine when we're changing multiple variables. So force equals k times mass times acceleration. Assuming the force remains constant. So now the force is constant, our constant is constant. It says what happens to acceleration when the mass is doubled. So if I double the mass, what happens to my acceleration? Well, remember, that's an equal sign. These two things have to be in balance. So to make sure we balance things out, my acceleration has to be cut in half to make sure these things remain equal. Let's look at the formula for the kinetic energy of a moving body. Energy, K for kinetic, because there's different types of energy. There's potential energy and kinetic energy. Kinetic energy is equal to 1/2 times the mass times the velocity squared. These are your variables. This is an actual formula. So let's assume that the mass remains constant. So the mass is constant and 1/2. You can think of this as our K. This also remains constant. So these two values remain constant. They don't change. What happens to the energy when the velocity is doubled? So kinetic energy is equal to 1/2 the mass times my velocity squared. Now what am I doing? I'm doubling my velocity. But if I double my velocity, notice I have to square that. So to balance things out, this value would here become 2 squared, which is 4. So to balance this out, the kinetic energy has to be multiplied by 4. So you can see right here, this is a direct relationship. However, as one value increases, the other value goes up significantly in size. Why? Because the variable is squared. Let's examine another situation. Kinetic energy equals 1/2 the mass times the velocity squared. So what happens to the velocity when the energy is increased by a factor of 25? So again, these values will remain constant. I'm increasing my energy by 25. So I have to increase this side by 25, but I'm increasing the velocity. What do? I multiply my velocity by 5. Why? Because you're squaring the 5. 5 squared is 25. So you can see you have to take into account these extra multipliers in some of these more complex equations. I would assume at the beginning of last lecture, when I asked you to write down as many formulas as you could think of, you wrote down E equals mc squared. What does that mean? This is a famous formula created by Albert Einstein. It relates energy to mass. Energy and mass, the theory is they are the same thing. And how are they related? Our constant of proportionality is the speed of light squared. Now, the speed of light is a very large value. 3.0 times 10 to the 8 meters per second. That's how many meters per second light travels. That's why you can take a little bit of matter, nuclear material, and create a bomb. A little increase in matter has a huge change in the amount of energy. That's one thing about science you have to understand, is that there are many amazing things we can do with our discoveries. We can create a lot of energy in nuclear reactors when we convert matter to energy. We can also use that same knowledge to build mass weapons of destruction. We're at the point now where we have to start deciding we can do these things, but should we? As an example, it is completely possible to clone human beings now. However, in the majority of countries, it is illegal to do such things. Same with things like CRISPR-Cas9. We can now edit people's DNA. That is now possible. However, the question is, should we do it? There will be more amazing technologies that are developed, and we'll have to have these discussions when that happens. Ideally, we start thinking about that now before it's too late to change things. I have 3 practice questions here for you. I'd like you to try them now. They're all in relation to this same value up here. I'd like you to read it through, write the proportionality expression, sub in your values, solve for k, and then find the unknown when you have the other values. Give that a try now. Let's take it up. Here I have S varies directly with R. So S varies directly with R. I then have S varying inversely with T. So the S is related to both the R and to the T. S varies inversely with T. I then have T varies directly with the product of P and the cube of Q. So I'm taking P, multiplying by Q, but not just Q, I'm multiplying by Q cubed. This looks a bit different. Let's deal with it one step at a time. Let's combine these together to build one equation. S is proportional to R divided by T. Let's now rearrange this to solve for T. So T comes up and S goes down. Now I will combine these two into one final equation. T is proportional to RP Q cubed over S. Many variables there. 1, 2, 3, 4, 5 variables and how they're related to each other. I have S, R, T, P, and Q. And I've asked to find the value of K. No problem. Let's do that now. T, I remove my proportionality symbol, write in equals K, R, P, Q cubed over S. Let's now rearrange and solve for K. So K is equal to T times S divided by R, P, Q cubed. Now that I have K solved, let's sub in the values we have. T is here, it's 2. S, right here, 5. On the bottom here, R is 3, P is 4, and Q is 2. Don't forget to cube it. Work this out now. 10 over, what do we have here now? 3 times 4 is 12. 2 cubed, 2, 4, 8. 10 over 8 times 12 is 96. We can simplify that down to 5 over 48. So I can build an equation here. T is equal to, I can write this 5 over 48 times R P Q cubed over S, or I can write that simply as 5 times R times P times Q cubed divided by 48S. Here is a formula that relates all those variables together, and I know my constant of proportionality. It's 5 over 48. Lastly, let's solve this. So I want to know what the value of R is if I tell you S, T, P, and Q. The formula I calculated earlier, T is equal to 5R P Q cubed over 48S. We want to solve for R. Let's rearrange it and solve for R first. So R remains here. I get R being equal to, the 48 comes up, 48 times T times S, and the 5, the P, and the Q come down. Sub in the values now, right? I don't know this, but I know these values here. So sub those values in. 48 times T, T is 1, times S, which is 3. Divide that by P. Make sure you put the 5 in there. And then we have Q, which is 1. Work that out now. 48 times 1 is 48, times 3, 144. 5 times 2 is 10. 1 cubed is just going to be 1. So this is going to be 10. Here we get 14.4. We can say these are not measured numbers. Therefore, they have an infinite number of significant digits. So our final answer here is 14.4. So hopefully you can see this is how formulas are created. We look at relationships in the world and see how one factor influences another factor. We can do experiments to collect data, and from that, we can determine the ratio of change between these two values. We represent that ratio of change using a constant of proportionality. From this, we can create a number of formulas so that people coming after us don't need to do those experiments. They can just use our data and the formulas we've created. In the previous lecture, we looked at only 2 variables affecting each other. In the real world, there are usually more than 2 variables involved in anything. But hopefully now you have an appreciation for how formulae are created. That's all for today. Until next time.